morning, everyone. Sorry for being a bit late. So this talk is about Async IO and all the lies surrounding Async IO. And I want to start by telling you why we're having this talk. So there's a lot of misconceptions around asynchronous frameworks, asynchronous technologies, blocking IO, and so on. But there is a new technology that changes everything, at least in the JVM world, about this interaction between async and sync. So we need to have this discussion, actually dive into what asynchronous means, what asynchronous means, and why is one of them better, or is it? Because now that we have Project Loom, which we will discuss at the end of the talk, we need to basically check again all of our assumptions about this topic. Okay? So I want to start by talking a little bit about concurrency and how computers work, how CPUs work in general, because this is essential to understand everything that's related to asynchronous programming. So basically, we have a CPU and other resources, and those resources needs to be shared between multiple processes or multiple tasks and so on. So it's really about concurrency. How do we do things concurrently? And there's a difference between parallelism and concurrency. Parallelism means that we're executing at the same time on multiple resources, like multiple calls, whereas concurrency basically means logical parallelism, or the sharing of resources. So the things look like they're running together, although actually in real time they're not running together. So we have some thread of execution, and basically, computation that runs has some tasks, and between the tasks, it has to wait for something to complete, something external. Presumably I/O, maybe from the network, maybe from a disk. You get the point. And we have several of those, and we want to share the resource between them. So what the scheduler does is it finds the spaces between the tasks, and in those spaces, it allows some other computation to run. So the scheduler gets those tasks, orders them in some way, puts them in a queue, and then schedules the jobs from the queue on the CPU or whatever it is that it's scheduling. So there is one question that is very fundamental for this kind of scheduling, which is how do we switch between tasks? How do we tell one task it needs to stop or pause or complete before we can put another task on the CPU? And there's basically two ways of doing that. One of them is preemptive multitasking, and the other one is known as cooperative multitasking. So what is preemptive multitasking? Preemptive multitasking basically means the scheduler forces the pause of the task that is currently running on the CPU. And technically, this is done by some hardware mechanism, hardware interrupt, timer interrupt. But it can also be done in several programmatic ways. Cooperative multitasking, in contrast, basically means that the scheduler has to wait for the task to say, okay, this is a good time to stop, I want to pause, here's the control back, now you can schedule another task. Okay? So usually there's some kind of programmatic call for this. It's often known as yielding. And you'll see this in a lot of languages. This is basically what await means, all the languages that have async await. But the problem is, what if a cooperative task doesn't play nice, doesn't yield, and if it doesn't give control back to the scheduler, there's no way for the scheduler to run other tasks. So the danger here that one task can hog the resource for itself. And we actually see this in a lot of cooperative multitasking operating systems and frameworks. You have to program in a much more careful way when you're running on a cooperative multitasking system. Now, there is a common confusion, which is async IO versus non-blocking IO, or async in general, non-blocking in general. They do not mean the same thing. And it's important that we talk about this for a bit. So, blocking and non-blocking, okay, those terms, actually mean function call semantics. They relate to how functions are called and how we get response to them and the amount of time and control that we have between when we call the function and when we get a response. Synchronous and asynchronous, in contrast, are a programming model. They encompass many different things other than just function calls. Things like how do we preserve state? How do we move between functions? How do we share context between different parts of the stack, and so on, so on, so on. So it's something that's much broader than just a function call. So blocking calls look kind of like this. We call some function, and then our execution, or logical execution, pauses until this function is done. This may be due to time consumed by the CPU, the amount of work that the CPU has to do, or it can be I/O. But in any case, we can't do anything until the function returns. Non-blocking means that we call the function, but the function doesn't necessarily do anything. Control returns immediately to us. We get some handler, or we give the function some callback, and then at a later time, execution proceeds when the function is actually done. This can be in 10 minutes, it can be in 20 seconds. We really don't know, but the upside of this is that we can decide not to proceed, not to execute further. So we have more control, but we don't necessarily preserve the order of things. So this is the main difference between blocking and non-blocking calls. Now, synchronous code, or actually synchronous programming model, is a model that preserves the logical order of things. Basically, it guarantees that things will execute in the way that they're written in the program. So it's very easy to understand what's running before what. This implies blocking functions, okay? Asynchronous code means that ordering is not guaranteed. We as programmers can decide on the order of execution. It's not necessarily the order in which things appear in our code. And this, of course, implies non-blocking functions. Now, both of those concepts are really quite meaningless, to not that different, if we don't have concurrency. So in terms of execution, if the concurrency is 1, synchronous code and asynchronous code will execute almost the same. There will be minor differences, if any. If you want an example of this, Lambda. AWS Lambda has a concurrency of 1, and even if you're running on node.js or Lambda, maybe you're writing in an asynchronous framework where your code actually executes kind of synchronously, or very close to it. Now, another way to put this is that synchronous model basically guarantees a logical clock. Okay? You can think about a clock that is in your program, and it's basically a counter that counts execution. And the synchronous model guarantees that this clock, the order of the clock, will be preserved in your program. The downside of this is that it breaks the relation between this clock, this virtual clock, and the real-world clock that we know from physical life. So if you look at the code, you don't actually know how much time, in terms of the real-world clock, it will take a function to execute or a block of code to execute. It can be any time, and really the scheduler decides on this. And a very good example of this is if you have preemption. Your code can pause for, let's say, 20 milliseconds or half a second even, and you can't see this on the code execution, or at least not when you look at the code. Okay? This is where we bring in profiling tools and so on to actually see what happened. As opposed to this, asynchronous code doesn't make any promises about the logical clock, so things can go back in time in terms of the logical clock, but it leaves control to you, which means that you can, if you want, keep synchrony with the real-time clock. Okay? So because functions are non-blocking, and control is still in your hands, you can pause at any time and look at the real-time clock and say, okay, I want to do this because too much time has passed, or I don't want to do this, and so on, so on, so on. This is useful if you're doing real-time programming of any sort, if you're building schedulers, if you need to handle delicate timeouts, and so on. Slides? Yeah, amazing. So just to give you the contrast again, synchronous is about, gives you state management, gives you resource tracking, gives you linear control flow, which is easy to understand, and back pressure, we'll talk about that in a bit. Asynchronous code is about timing control, precise timing control actually. It has sparse control flow, which is usually something we don't want because it makes programming harder. And it's minimalistic, which allows us to get more performance in extreme cases, but of course, with great power, as we say in ops, comes no responsibility. So, Now, I want to talk a little bit about the lies surrounding all of those topics. So, first lie is threads are synchronous. This is what is known as a damn lie. You know what a damn lie is? A damn lie, as opposed to a normal lie, is something that has some core of truth, but around it we build a lie. So the lie here is that actually it's a confusion. Okay? Synchronous and asynchronous models are an abstraction. And the implementation can be many things. The implementation can be blocking, it can be non-blocking in terms of how it's implemented internally and what APIs it uses, what kernel APIs it uses, or what I/O APIs it uses. So just to give you a few examples, Golang, which is known for its high concurrency framework, is often cited as asynchronous. It's actually a synchronous model. The model is known as CSP, or cooperative sequential processes. Sequential basically means synchronous. Okay? So Golang is actually a synchronous abstraction. It's built on top of a user-learned scheduler and uses the non-blocking API of I/O API of Linux. As opposed to this Java futures, which are usually backed by executors, threads, are an asynchronous abstraction that it's built on top of kernel scheduler threads, which basically means blocking I/O. Okay? So you can actually use different implementations, blocking or non-blocking, and create asynchronous or synchronous models on top of them. So we need to understand the difference. When we talk about synchronous abstractions, we usually talk about threads. This is distinct from kernel threads. This is known as an execution thread. And this is the primary abstraction we work with. It represents a single serial job, and all operations from our point of view are blocking. And this includes I/O. It's a very handy way to deal with I/O. And if we need concurrency of some kind, then we just use multiple threads. Okay? This is basically why we have futures. The really cool feature about this is the stack. The stack preserves the state and basically allows us to share certain things within all the functions that execute on the same thread. Okay, if you've seen thread locals, if you use them, this is how it's implemented, basically. Now, just to give you examples of the confusion, this is asynchronous code, but is using threads, okay, Java threads in this case. Okay, executor submit, you've probably all used this. This is asynchronous, but without threads, okay? Completable future, again, from Java. Probably you've used this. Many people use it in Netty and so on. So this is async without threads. This is synchronous code without threads, okay? It looks just like the code, like the normal synchronous code, but it doesn't use threads. How? We'll talk about that in a bit. So the lesson here is that we need to be very careful about the terminology that we use when we have those kind of discussions, because it makes all the other discussions about performance, reliability, features, and so on very bad. It's very hard to have an engineering discussion if all the terms are confused. Okay? So computation threads are not the same as execution threads or tasks. Okay? We need to be very careful about this. Now, this is one of the most famous lies about asynchronous and non-blocking I/O, that it is faster and more efficient, and we should all be using it because it's so much better. Is this true? So the lie goes kind of like this. Asynchronous is fast, synchronous is slow. Why? Because threads are expensive, and if you use threads or blocking I/O, or actually kernel threads, context switches will kill you, it will kill your performance. Well, that's not exactly true. Let's have a frank talk about performance. Okay? All frank talks about performance start kind of like this. It's complicated. Okay? So, what is performance? Is it average? Is it 99th percentile? Is it latency? Is it throughput? Can you actually achieve all of those together? So when we start to talk about performance, when we start a conversation about performance, it's really important that we define what is performance for us. Okay? What is the metric that we are trying to optimize for? So just to give you an example, those are two latency curves. Okay? So this is like the histogram of the latency curve of two, actually the same server, okay, implemented in two ways. This line is the histogram. You have the red and the blue. And those lines here are the 99th percentile. Now, as you can see, the red curve has, well, the peak is slightly faster, the average is faster, but the 99th percentile is much higher. The blue line has slightly slower average, slightly lower, slower, even like peak, but the 99th percentile is lower. So, depending on what metric we're trying to optimize, we might say that the blue line is faster or that the red line is faster. And actually, in this case, the blue line would be the synchronous framework, and the red line would be the synchronous framework. Okay? So, is any one of them faster? It depends. So, actually threads, and I actually mean kernel threads, perform better on specific tasks. When we're talking about CPU-bound workload, usually we prefer threads. Why? Because preemption. Preemption, as I mentioned before, basically means that no single task can hog all the resources. At some point, the scheduler will evict the offending task from the CPU. So it's better for quality of service. It's better for allowing other threads to run. Okay? It also has a very nice feature we'll talk about in a bit, which is called back pressure, which is important for load management and working with high load. So if we wanted to have the same features with some kind of a synchronous framework, which is often implemented on top of an event loop, event loops don't have quality of service. They don't have this feature. Okay? You can think of the kernel as a very complicated and very elaborate event loop. Okay? So in the kernel, because a lot of work has gone into the kernel, they have actually implemented quality of service and all that stuff. There is no technical barrier for implementing that kind of stuff in other event loops if, and it's a big if, the underlying technology, in this case the kernel, allows that. So we'll talk about that in a bit. Now, what is the overhead of threads? Again, one of the major myths about threads. So many people don't know. I went and actually measured. So on my laptop, okay, so native threads, kernel threads on Rust, C, native languages like this, default to 2 megabytes. The minimum is 16 kilobytes. Just to give you a reference, Go routines are around 40 kilobytes, so it's actually less. Okay? And the time to launch a new thread is about 10 to 15 microseconds. That's not a lot. JVM is a bit more expensive, so the default stack for JVM threads is 1 megabyte. You can get it down to around a quarter of a megabyte. The launch time is much higher. It's about 40 to 100 microseconds. And in terms of throughput, I got to 20,000 threads per second without breaking a sweat. I could probably go higher, but there was no point. Okay? So if you compare this to, let's say, the latency of request of a normal server, let's say that the latency of your service is, let's say, P99 or 50 milliseconds, you could spawn a thread per request, not even use thread pools or executors or anything of that sort, and it will be negligible. Okay? So, not so expensive, really. What about context switches? So, the cost of a context switch actually changes a little bit depending on the type of context switch. There are a few types. But the most expensive one today on modern hardware costs less than 5 microseconds. Okay? So that means that CPU core can run about 200,000 context switches per second. We don't want to get there. If we got to even 20,000 context switches per core, it means that you're wasting about 10% of your CPU just on task management. You don't want that. But if you run VMstat, you can actually see how many context switches you're doing. And you can see that normally it's not a lot if you're not overloaded. It's in the range of a few thousands. Okay? So, again, the overhead is not as big as people think. It's sometimes bad if you're doing very delicate I/O work, let's say you're writing a database. But if you're running a web application, normal business application, you shouldn't care. Okay? Now, when would you get excessive context switches? There are only two let's say, occurrences, two conditions that will make your code have a lot of experience, a lot of context switches. One is that you exhausted your time quantum, meaning the time that the kernel allows you to run your task on the CPU. And the other one is that, so basically the kernel will boot you off and will do a context switch, and the other condition is that you evicted yourself, basically yielded control back to the kernel, and the kernel will switch you to another, and will switch the CPU to another task. Okay, so the only case where you would have excessive context switches is if you are overloaded. You have too many threads competing for the CPU. Let's say you have 1,000 threads or something like this, and they all need the CPU at the same time, meaning you're not doing a lot of I/O. Okay? In this case, yes, you will be overloaded and you will have too many context switches. But this should never happen if you're managing your server correctly. So the question that often rises is, how many threads should we have? And there is, in fact, a formula for this. And this formula relates to the ratio between I/O weight and CPU time. Okay? And from this, you can see easily that if you're using 90% I/O and then 10% CPU, then you should have 10 threads per core. Now, you would notice something about this formula. It doesn't mention threads. This formula actually talks about concurrency. We actually have the same problem with asynchronous frameworks. Okay? It really doesn't matter in terms of concurrency and performance. What you use, this ratio still holds. The only difference is who's doing the context switch. Is it the kernel context switch, which is slightly more expensive, or is it the user-land context switch, which is slightly less expensive? But if you overload your server, you will have problems. If you run concurrency that's higher than this, you will have problems regardless of if you're using threads or asynchronous. Now, the motivation behind all of this came from something known as the C10K problem. This was drafted in the 90s, and loosely speaking, the problem is this. How do you run a very large number of concurrent connections or serving concurrent clients on a single server? Okay? So back in the day in the 90s, like the holy grail was, how do you serve 10,000 concurrent connections? Like, whoa, that's so many. That's the entire world of the internet. But then in 1999, okay, first reported success, cd-rom.com, nobody remembers that, of course, from the bubble days, reported they were able to reach 10K. 12 years later, WhatsApp, okay, was running 1 million concurrent connections on a single server. They did it with Erlang and BSD. Look it up. It's very interesting how all the optimizations they needed to do this. 1 year later, they were able to double it. Okay, that's quite amazing. 2015, we already got to this insane number on Java and Linux, 10 million, so 10 times improvement. And slightly later, 12 million already. This was almost a decade ago. So just imagine the numbers we can get to today. Okay? Is anyone here running 1 million concurrent connections on a server? No? 100,000? Oh, we have one. That's about it. Okay? So those are the numbers for which asynchronous frameworks were created. If you're not running this, like at least order of magnitude, you can do with threads. It will work. Trust me. I've done it. So let's move on to another lie. Async is better. And again, this is a lie, and the reason why it's a lie is very simple. What is better? Better is very contextual, right? So this is asynchronous code. This is what it looks like. This is from node.js. I hate it with a vengeance. There's a JavaScript conference in the same place a few months from now. You can come and hear me rant about JavaScript if you really want. But just look at this mess. Who wants to program like this? The reason why it looks like this is because we have what is known as a callback hell. We have an async function that calls a callback, that calls another callback, that calls another callback, that calls another callback, and looks sort of like this, like someone pushed a fireball and pushed all the stack. Okay? There's nothing good to say about this. So we need something better, obviously. And of course, there has been a lot of work in programming languages to hide this hole and switch it to something more manageable. So one of the main features that we get from synchronous frameworks is context. Transparent context that basically moves with the stack and is available from all the functions of the thread. If you use log4j2, this is from log4j2, thread context basically allows you to put stuff like request ID, user ID, and so on, and it will be magically logged from whatever logging statement you have. Most of the logging frameworks in Java have something like this. This is implemented using thread locals. In newer JVMs, we have something even cooler, which is the same as thread locals, but has basically like hierarchical spaces. Look it up, it's really cool. But this is a feature that we really want for tracing, for logging, and for many other things, and exists by default in all the synchronous frameworks. In Node.js, where they didn't have this, they had to work really hard to create this kind of feature. In Golang, they still don't have it. Instead, they pass a context object. Now, what is the problem with a context object? One, libraries, they don't support this. They don't have a parameter for the context object. Second problem is, if you need to refactor and add a context object, you need to refactor all of your code because all of your functions have to have this parameter and provide this parameter to all the functions they call. So almost impossible to do. Now, in terms of load management and concurrency control, with threads, it's very easy to do. Okay, so this is a basic queuing theory diagram. Okay, this is how latency and queuing behaves on load. So when a server becomes loaded, close to 100% utilization, latency starts to reach infinity. Okay, how do we deal with this? We limit the utilization, or we limit the concurrency of a server. How do we do this with synchronous frameworks? Very easy. We limit the number of threads. We're done. Okay. If you have an executor or a thread pool, you put the number there, 10 is the maximum, we calculate it using the formula we've shown before, that's it, we're done. How do we do this in async frameworks? Problem, okay? We need to keep some counter, we need to manage it ourselves, we need to maybe run some other mechanism, and it's much more complicated. So Little's law, okay, again from queuing theory, basically means, you all know this, maybe not with this notation, it means the concurrency equals the throughput times the latency. That's what it means, okay? So, So basically, if we don't want to run into overload, we can limit either the concurrency or the throughput, okay? Latency, of course, we don't control. This is done using back pressure. Okay, so what is back pressure? The incoming load from the client is known as the forward pressure. Okay, and forward pressure is applied from the client to the load. We call a thread pool, we apply pressure on it, thread pool applies pressure to more thread pools, and so on, so on, so on. Somehow we need to tell the system, the client, that deep within the stack, there's been overload. There's no way for the load balancer or the client to know that it overloaded your database or one of your thread pools. Okay? So we need to transmit this information backwards, and this is called back pressure. Okay? So with blocking, it's very easy. If I block, whoever called me blocked, whoever called them blocked, and so on, so on, so on. It's a chain of blocking that terminates at the client, and then the client blocks and doesn't send any more traffic. So with blocking call semantics and synchronous frameworks, we have back pressure by default. We don't need to do anything. Okay? We just need to make sure we don't have anything asynchronous in the middle. With asynchronous, it's much more complicated. We need to somehow implement this ourselves. There are ways to do this. Look for reactive streams, for an example. But basically, the idea is always this. We send some acknowledgement backwards. Okay? This is how it's implemented in network protocols, which are inherently async. So look at TCP back pressure, for an example. Now, this is very important when you're doing microservices programming, because the chain of back pressure has to be preserved. If one of the microservices, one of the parts of the system, breaks this contract, the back pressure of the system as a whole will not work. Okay? So I'm sure most of you had this problem where one of the servers or one of the services had suddenly a queue that goes to infinity because it doesn't preserve back pressure. Or maybe one of the servers deep within your stack, the event loop goes to overload or something like this. This is a classic things that happen when back pressure is not preserved. In addition, resource monitoring, debugging, all of that stuff, resource accounting, is so much easier when you're using synchronous things. Why? Because the threads basically have a root of everything that was allocated or related to the thread. Very easy to see how much CPU a single thread consumed, which should map to how much CPU you spent on executing a client request. And we actually want to know these things, especially in the world of FinOps. How much did a client transaction cost? Okay? What is our unit economics? Okay, those kind of things. How much memory did we spend on a single client request? Again, very, very easy to know with threads because every thread is a GC root. This also helps the performance of the garbage collector, by the way. You get the point. Who called what when is very easy to do with threads. How do we do this with sync? Very hard. Why? Because if you look at the stack trace of a synchronous framework, everything is broken, like the stack is broken, and all starts from the event loop. Okay? So not easy to do. How do we preserve resource accounting? We have to do it ourselves. Remember, a synchronous framework, the whole point of a sync is it's minimal. It gives us more control, but it lacks features. So, what's going on with this? So let's talk about non-blocking I/O. Yes, it's all lies. There is no true non-blocking I/O in Linux. Okay, so if you're using BSD or one of the other fancy operating systems, maybe you have this, but on Linux you can forget about it. For many years we didn't have true non-blocking I/O in Linux. I'm not going to go too deep into this. If you want to hear me rant about this, you can come talk to me later. In recent years, about 2 years ago, the kernel got a new mechanism called I/O Uring, which is true non-blocking I/O in Linux. Thank God. The only problem is none of the runtimes actually use this. So it's coming to JVM sometime, maybe next year, maybe the year after, but right now there's no implementation in the JVM that uses this. So really, you're using blocking I/O. This creates a lot of problems. Yeah. So all of the performance benefits that people promise you from asynchronous coding, well, you maybe can get them, but really not on Linux, not without very hard work. But the lies actually contain a core of truth. Okay? Yes, synchronous is sometimes better. Okay? And non-blocking is sometimes better, even on Linux. So what's wrong with the synchronous model? Okay? Two major problems. One is that time is implicit. Remember, I talked about this at the beginning. Real-world clock, okay, from the point of view of synchronous model, doesn't exist. This means that if we're trying to do some timing, like maybe we're doing real-time programming, or we actually care about our timeouts being preserved and so on, not in synchronous model. It doesn't allow it. Okay? Also, it's expensive because it makes a lot of nice promises. It gives us a lot of features. Features have cost. Okay, so it's more costly in terms of resources. This is basically the opposite of minimalism. But actually, the model is pretty good. The real problem is that the implementations suck. Okay, so just to give you an example, if we implement it in user space, like they do in proteins and fibers. You can find this in many other languages, like Golang, or Ruby, or Python, and so on. It costs much less to create a new fiber than it does to create a new thread, which is basically equivalent. Also, less in terms of memory. So, in JVM, we have a one-to-one mapping between JVM threads and POSIX threads. This is the underlying implementation of what we know as threads. And the problem with POSIX threads is that they have been designed in the 90s. Again, not very big surprise. They made a lot of assumptions that were true at the time. Assumptions about cost, about resources, and so on, so on, so on. So back in the day, if you use magnetic disks, the seek time of a magnetic disk is about 10 milliseconds. Context switch of 5 microseconds, or even 10 microseconds, compared to 10 milliseconds disk sake, not a lot, right? What happens if you have SSD or NVMe? I/O time drops to about 50 microseconds or less. 5 microseconds context switch in comparison is eternity. It's like horribly expensive. So this assumption has been completely broken. There are many more assumptions that were broken as a result. Assumptions about concurrency, how many threads you run on a single server, and so on, so on, so on. So if we actually want high concurrency, if we actually care about cost, then this becomes a real problem. How do we know that POSIX threads suck? Thread pools. Everybody's using thread pools. The original model of synchronous programming actually says you should be using one thread per task. You should initiate it when this task starts, and you should shut it down when it ends. Okay? We should not be reusing threads. That's a violation of the model. This is why if you look at the API of threads, you can start it, you can stop it, but there's no way to restart it. Okay? The API doesn't have it on purpose. So this is really a proof that we have failure of the implementation. So we have a dilemma. When we write a JVM service or some other backend service, we need to choose between shitty abstraction or crappy implementation. I don't know about you, I hate this choice. Do we actually have to have this horrible choice? Maybe we can have the best of both worlds. And this is where Project Loom comes into the picture. So Project Loom gives us user-land threads in the JVM. So what are user-land threads? Basically, the stack we use today is composed of many layers. We have the hardware, we have the hypervisor, we have the kernel, the JVM, the runtime, and our code, and of course the libraries we use in our code. And actually, we can implement the scheduler and the concurrency in any one of those layers. What does a hypervisor do? It shares multiple virtual machines on a single machine. How does it do this magic? How does it do this magic? It has a scheduler. How does the kernel allow multiple processes to run on the same virtual machine? It has a scheduler. Java can have a scheduler. Amazing. The higher we go in the stack, the more control we have. Okay? Because we know more about what the tasks are going to do, how memory is allocated, and so on. So in terms of performance and the quality of the abstraction of the implementation, it makes sense to implement this as high as possible. So we want to move from the kernel space scheduler to a user-learned scheduler in the runtime. So remember, abstractions are not the same as implementation, which is why it's better to have this discussion about performance and all that stuff in terms of kernel scheduler versus user-learned scheduler, and of course the semantics of the I/O calls that we're actually doing. Okay? The performance really depends on the implementation, not the abstraction. Which means that we can have synchronous abstractions that perform very well. And this point has been made a long time ago by none other than Eric Boer from the CAP theorem. There was a symposium about 20 years ago that talked exactly about this. And basically they said asynchronous programming is a bad idea even for high concurrency servers. Why? Because all the reasons we mentioned before. And there is no technical reason why we can't have the performance of asynchronous programming with the synchronous abstraction, with some changes. Okay? Mainly, tight integration between compiler and runtime. Guess what we have in JVM? We have tight integration between compiler and runtime. Amazing. So we get Project Loom. Project Loom basically means that now the threads are no longer coupled one-to-one to kernel threads. We can have a mapping between a small number of kernel threads, one per CPU, or one per core actually, or slightly higher than this, and any amount of user-land threads that we want to spawn. Okay? It has exactly the same API as threads, so you don't need to change your code. Everything will just work magically, more or less. And you get high performance and very, very cheap threads. Okay? How cheap? So cheap you can spawn them for practically anything. You can spawn a thread that does like two things, like go to some HTTP endpoint, get some response, do this with a concurrency of 1,000 or whatever, and it will work magically. It is not a good fit for CPU-bound labs. Why? Because it's not preemptive. Okay? So, just to give you an example, this is Project Loom. It looks exactly the same as normal programming, except for the line at the start, which says start virtual threads. Virtual thread. So if you spawn an executor, this new virtual thread executor, or do this thread constructor, that's it, you're done. Performance magically improved. So there are some current issues. It's not perfect yet. It's brand new. It just came out in Java JDK 21. It's still improving. It will improve over the next few years. Those are like the main problems to avoid. There's also some other differences that are worth looking at. I'm not going to talk too much about this because this is not a talk about Project Loom, but there's a lot of information about this in the internet. Synchronous, particularly, is like kind of like meh at this point, but it is improving. And I/O, of course, if you're on Linux, like I said, it's lies. But it's good enough for almost everything in the JVM. So with that, I'm done. Come talk to me afterwards if you want to discuss more about the lies and the synchronous programming and node.js and how much I hate it. And thank you very much.